Bismillahirrahmanirrahim. Assalamu alaikum, all students. This is your first lecture of Fundamentals of Electrical Engineering. I am your instructor, Muhammad Hassanul Haq. Let me put that for you. So I would be teaching you this course. I would be teaching you this course in this semester. And this course has been offered by the Department of Electrical Engineering. I'm an instructor at the Department of Electrical Engineering, and this is a fundamental course that would teach you about electric circuits, electrical machines, and some magnetic circuits. So this is a very fundamental course. It has a very broad course outline. We are going to quickly talk about that course outline, but before that, let me put for you the the way in this course is going to be delivered. So you understand this is going to be an online kind of semester, and we are going to stick with uh, the different methods of online teaching. In that regard, I would like to ask you that you must give us the teachers, give me, for example, as your teacher of fundamentals of electrical engineering, give us your feedback through the discussions on the Google Classroom. So feedback is going to be really important. You should be able to hear us clearly. So audio, is it clear or not? You need to tell us about that. Similarly, you need to tell us about how the visuals are. If you can understand, you can see that particularly my writing is not that good. I'm trying to put things as cleanly as possible. So all the visuals are going to be important if I'm using diagrams or if I'm using PowerPoint presentations. So you need to give us feedback about that. And also you need to give us feedback about your ability to connect to the internet and get the lectures. So connectivity is also very important. We are going to have live sessions also every week. So your connectivity for downloading and your connectivity for connecting to the live session is very important. So these are the different aspects. Let me adjust the volume first, and so that this becomes better for you. Okay, so the course is fundamentals of electrical engineering. It's a fundamental course. It's about electricity. What are its main and important areas? Let me put that down for you. Now, before I put that down, I must tell you that there are handouts available on the Google Classroom. So please don't forget to get those handouts. And the material that I'm sharing here and explaining here in the videos is also available in the handouts. So just in case you need to fall back to some equation, or just in case that I have written something wrong, you can easily refer back to the handout. So let's quickly jump to today's class. The first thing is that you might have some perception about electricity, and in that regard, um, when we talk about electricity, we do talk about different aspects of electricity. So in this course, let me put the outline here for you. So course outline. In this course, we are going to talk about different aspects of electricity. The first one, and the most elementary one, you have already seen this, is we are going to talk about DC circuits. DC stands for direct current, and you know that direct current has many simple available sources in our homes. Direct current is that kind of electricity that flows in just one direction. It does not change its direction. That's why it's called direct. And it's available through batteries. It's available through more recently it has become available through solar panels, and the direct current systems are also present all over the automobiles. So all cars and different kind of automobiles also run on direct current type kind of electricity. In the cars, however, there exists something called a DC generator. So the source of electricity in a car is not essentially a battery. There is a battery for backup, but it's mainly DC generator. So these are direct current circuits, and DC circuits are the easiest kind of circuits to analyze, and we are going to look into that in this course. The second kind of circuits, or the kind of things in electrical engineering that we are going to talk about in this course, are going to be AC circuits. The second topic would be AC circuits. AC circuits, short for alternating current circuits. Alternating current circuits are the circuits that we use in our homes in daily lives. So your light bulb runs from AC circuits, your refrigerator works on AC circuits, and there are all the home appliances that we can name. However, the source of these circuits, the source from where you can drive alternating current, is not a battery, and the source is called an AC generator. Now, we do have those also in our homes for backup when the electricity from the company is turned off. Those are single phase, one phase generators, and then the power company supplies you with electricity using three phase AC generators. That is the source for alternating current. Frankly speaking, there are no natural sources, and there are no sources of AC circuits which are stored. You can see that in DC circuits, you have batteries. Batteries can store energy. Unfortunately for AC circuits, there is no storage available. AC is always generated when it's needed. You cannot store it in some kind of backup system. So that's the kind of basic difference between these two kind of electricities. You also know that the DC, if you're talking about drawing the diagram, for example, this is voltage with respect to time. The DC voltage is just a flat line. For example, this is a 12-volt battery. In that case, the flat line will be exactly on 12 volt. And for the AC circuits, the voltage is not going to look like that. It's going to look like alternating. So it's like this, a sinusoidal wave. And uh, when we talk about 220 volt AC circuit, so it actually doesn't mean that the peak of this alternating voltage is at 220. We are going to talk about it later in great detail. 220 is not the peak of the AC voltage. You might be thinking in DC voltage, if it's a 12 volt battery, the voltage line, if you look at its graph, it's going to be on 12 volt. That's right. But for AC voltages, a 220 volt AC voltage line does not mean that the alternating current, which looks like this, has a peak of 220 volt. It does not have a peak of 220 volt. The 220 volt is somewhere else. We are going to talk about that when we start AC circuits. The third kind of circuits that we are going to study in this course are slightly different. They are called magnetic circuits. Now, magnetism is something you have studied the basics of magnetism. Um, there are natural magnets. So there are natural, or you also call them permanent magnets. And there are also something of a different type there, which are called the electromagnets. Even though the behavior of the two kind of magnets, the first kind, which is the natural magnet, and the second kind, which is the electromagnet, is kind of the same. Electromagnet is particularly useful because we can control it. So, you know the basic electromagnet. You all have seen that. If you have a current coil, for example, if you take a piece of wire, you turn it around into a coil, and then, for example, use a battery to power that coil, this coil now becomes an electromagnet. This is the idea of electromagnetism. So some magnetic field B is going to be coming out of the coil. And we are going to talk about that as well in this course. So the electromagnets are the most useful kind of magnets. We talk about how to use them in different kind of circuits, and those circuits are going to be referred to as magnetic circuits. We are going to talk about them also in this course. Finally, the last topic here is going to be in this course outline is going to be, let me put down here. Oh, just a moment. I just forgot that there is another special kind of magnetic circuit that we use a lot in our homes, and you might have seen it everywhere in your home. Not directly, you cannot directly observe it. It's present inside every device, and this special kind of magnetic circuit is called a transformer. So a transformer is a piece of metal which has these four sides, which are called the members of the transformer. And on two of those members, you have similar windings as here, as you can see here. So you put on windings, you turn wire around two of the members of the transformer, and you have a certain device that can transfer magnetic energy from one end to the other. The interesting thing is that this part is electrical. This part is electrical. There is going to be some electrical circuit over here. There is going to be some other electrical circuit over here. However, in between, inside the transformer, there is no electrical connection. Everything here is isolated and insulated. So only magnetism B, magnetic field B, can flow through the transformer. So a transformer is a very useful device. It's a kind of a magnetic circuit that's used a lot in electrical appliances. We are going to talk about that. Finally, the last leg of this course would introduce you to the electrical machines. Now, some electrical engineers say that electrical machine is also a magnetic circuit. because all electrical machines work on magnetism. You already have seen DC motor in the intermediate course. You have already studied that. So all electrical machines are magnetic circuits, but they are slightly different. They are magnetic circuits that can rotate or move. So we are going to talk about the different kind of electrical machines, the AC motor, the DC motor, the DC generator. The essential kind of design. You have already seen that in your intermediate courses, in your high school courses. You know that, for example, um, the DC motor kind of looks like this. If you have ever tried to disassemble a DC motor in your home, in from anywhere, from your toys, for example, you might have seen that it has this kind of a construction, that there is a north pole magnet, there is a south pole magnet. Actually, there are just two pieces of magnets. I'm writing north and south because they are put inside the motor in that way. And then there is this you can call it a metallic cylinder kind of thing, which is actually called the armature. We are going to talk about that when we study this. And on this metallic cylinder, you have lots and lots of wire wrapped around. This is which is called the winding. And two wires come out of the motor on which you supply the voltage. So this is the elementary DC motor. We are going to talk about that in this, and furthermore about the other kind of motors that are available. So this was the quick overview of this course. It's very important that you understand these concepts. The overview is important uh, in all of its aspects. Don't think that this is not important, and you are not going to be asked questions regarding it. Now, I'm going to cover some of the prerequisites of this course. Uh, you might have already seen those, but I'm going to just quickly cover them so that when you start learning, uh, these topics don't bother you and we don't have to discuss about that. I don't want to discuss the prerequisites that you have already learned in intermediate or in A levels, O levels, and I don't want to discuss them uh, again and again. So let me put down the prerequisites of this course, some of the prerequisites. And I think this is an exhaustive list. I don't think we would need anything else. So we have 5 prerequisites in this course. You need to learn them, and you need to understand that these 5 prerequisites must be understood and kept in your mind at all times. Number one, this is the kind of the simple one. So we are going to be able to solve system of algebraic equations. Okay, so solution of system of algebraic equations. Now, this is the first prerequisite. Now, let me explain why this is important, and then I'm going to talk about the kind of prerequisite that we intend to do with this. Uh, all AC or DC circuits that we are going to study in this course, for example, this circuit or any other circuit, I'm not solving it right now, but let me make that circuit. All circuits, AC or DC, they are going to end up as a system of algebraic equation, a system of linear equations. So for example, this system ends up in equation a11 x plus a12 y plus a13 z is equal to b1, equation 1. Then similarly a21x plus a22y plus a23z equals b2. And similarly a31x plus a32y plus a33z equals to b3. Now, this is not going to be some kind of a hypothetical system. Here, the A's are going to come from the resistor values. The resistors, the capacitors, and inductors are going to end up here in the form of coefficients. X, Y, and Z are going to be the unknown voltages or currents. And B1, B2, B3 would become the known voltages or currents. You are going to see that when we perform analysis. But eventually it would end up in this way. It's going to look like a system of linear equations. So you need to remember that this can be solved, and you can easily put this system of linear equations as a form of a matrix. So let me put it in that way. If I put it in a matrix form, I can say A11, A12, A13, A21, A22, A23, A31, A32, A33. This is the first matrix. If you multiply it with the matrix with entries X, Y, and Z in one row, you can clearly see that this line A11 would multiply by X, then would be added to A12, which is multiplied by Y, and then that would be added to A13 multiplied by Z, and you are going to end up with this first line. So this system of linear equation can be easily transformed into matrix. And finally, the right hand side would be simply the row matrix, the column matrix B1, B2, and B3. And in short, we usually write it like this is called the matrix A, the matrix of coefficients, the matrix of unknowns X, and the matrix of constants B. You have A X equals B. Now here, the unknown that we are interested in solving is X, and you know that we can multiply A inverse to both sides. That's the proper way of doing maths. So if we multiply A inverse to both sides, we are going to get A inverse multiplied by A times X is equal to A inverse times B. And the resultant would be here on the left hand side, A inverse and A would multiply to give you the identity matrix, which won't be helpful in using. So the left hand side is left with X equals A inverse B. Now this is the most important part. In all AC or DC circuits that we shall be analyzing, you would need to find inverse of a matrix. So how are we going to do that? First of all, let me clarify that our matrices would be mostly 3 by 3 or 4 by 4. That makes things a lot easier. Secondly, let me tell you that 3 by 3 matrix, you are allowed to use calculators to solve those. I know that the Casio calculators, the FX series, I think 570 and 970. So this is the basic one which allows you to solve matrices. There might be other like Canon or Texas Instrument calculators that allows you to do that. But I know that this calculator, which is commonly available, can easily solve 3 by 3 matrices. However, 4 by 4 cannot be solved. So whenever we are going to encounter a 4 by 4 matrix, and if your calculator does not allow you to solve it, then you are going to use substitution to reduce the system into a 3 by 3 matrix and finally solve. I'm going to uh, give you the method, the detailed method in the handout, but it's quite simple. You have 4 equations, use one of them and take out the variable, one of those variables, and substitute into the remaining 3 equations, and hence you are going to get a 3 by 3 system. I have solved that in the handout. You can look at in the handout and you are going to see how the 4 by 4 system is going to be converted into 3 by 3, and then the rest is going to be worked on the calculator. So this is one of the prerequisites that you need to know. By the way, you might be thinking that what happens when A is not invertible? Because you know that when the determinant of a matrix is negative, then A cannot be inverted. The answer to this question is this would never arise. This condition would never arise. And the reason is we are solving real world circuits, and real world circuits do not result in non-invertible matrices. Only hypothetical mathematical questions would result in that. So if you are solving a circuit and your calculator is saying that the matrix cannot be inverted, then it means that you have solved the circuit wrong. The equations are wrong. Note that. The second important prerequisite that we are interested in is we need to understand this second prerequisite, and that is you should be able to understand complex numbers. Now, you have already understood the basics of complex numbers in your intermediate high school course. I'm going to quickly clarify a couple of points. The first thing to understand is that uh, when we use complex numbers in engineering problems, especially in electrical engineering and electric circuits, our understanding of the complex number is slightly, you can say, shifted. It's not different, but we look at them in a different way. So you remember that there is this real number line. Okay, so the center is at 0. Somewhere on the right hand side would be infinity, and along the left hand side somewhere you would find minus infinity, and this is the real number line. You call it real number line. So you have already seen this, and it contains all the numbers between minus infinity and infinity. It contains rationals, irrationals, every kind of number that you can think of. Complex numbers, on the other hand, are not represented by the real number line. For complex numbers, you need to have a real number line on the x-axis and another real number line on the y-axis. And in order to differentiate between the two real number lines, you use the notation iota on the vertical axis. The horizontal axis is same as before, infinity to minus infinity. Even the vertical axis works in the same way. On the up side, it's going to be infinity times iota, and on the bottom side, it's going to be minus infinity times iota. And the remaining line characteristics are the same. However, now the number is not on a line. On the left hand side, in the real plane, in the real number line, you can see that any number, for example 3.5, is just a dot on the line. However, if you talk about the complex number here, so this is called on the left hand side we call it the real number line. On the right hand side, since there are two lines which are intersecting at 90 degrees, it constitutes a plane. So we don't call it complex number lines, we call it the complex number plane. It's a two-dimensional thing. And here the points are not going to look like that. The points here, for example, this is a number. This is going to be, for example, 3, and according to vertical axis 2. So this is going to be represented as a point on a plane. You can write it either 3 comma 2, or there is another way of representing it, which is 3 plus iota times 2. This iota, you can see now clearly, stops you from adding 3 and 2, because the 3 is on the real number line, which is one dimension, and the iota is on the vertical line, which is another dimension, and both the dimensions do not relate to each other. This point exists on both of the dimensions, but the dimensions themselves do not relate to each other. Let me tell you a quick interesting fact, that whenever there are two variables or two kind of quantities that do not relate to each other, that have no uh, the two quantities have no relationship with each other, then you are actually dealing with a kind of a complex number. That's how complex numbers are actually used. So this is one aspect of complex number that you must understand. There is another aspect, that this representation of complex numbers, you can write it like this. This is the point representation, or you can call it the Cartesian point, because this looks like the complex number plane looks like a Cartesian plane. You can call this representation a Cartesian point representation. However, this one is called rectangular representation. There is another way of representing this complex number, and it's by using the theory of vectors. So if you draw a line from the point to the origin, and you make an arrowhead over here, just like a vector, and then you specify the angle between the vector and the horizontal plane, let's call it theta, then you have a kind of a polar representation. Polar representation of 3 plus iota 2 can be calculated using the formula. The polar representation would be, there is going to be a magnitude of the vector, and then there is going to be an angle of the vector. So the magnitude is calculated using square root of the x component squared plus the y component squared, and the angle part is calculated using simply the tangent inverse of y part of the complex number over x part of the complex number. So in this case, what's going to be our solution? It's going to be under the root, 3 plus iota 2 is going to end up like under the root 3 squared plus 2 squared, and the angle is going to be tangent inverse 3 by 2, 2 by 3, sorry, 2 by 3, because the 2 is the y part and 3 is the x part. So this is the representation of the same number, the same complex number, in the rectangular method and in the polar representation method. Now, we are going to use both of them, because you might have already seen in your previous classes that polar representation is good for uh, multiplication and division. You can quickly do that. in polar representation. However, the rectangular representation is good for addition and subtraction. That's why we need to understand both of them. You're going to see how it's going to help you in solving alternating current circuits. So AC circuits are going to use a lot of complex numbers. Now, the third thing, the third prerequisite that I'm going to talk about in this first lecture is some derivatives and integrals. So there are going to be some common derivatives and integrals. Let me write it here first. The third prerequisite is some derivatives and integrals. Now we are going to use a lot of derivatives and integrals when doing circuit analysis, DC circuits and AC circuits. I'm going to use a lot of those, but unfortunately, you won't be allowed to use a formula sheet. So you need to remember these in your mind. And these are quite simple. I hope you already know these. So let me just put them down. So d over dx of x to the power n is equal to n x to the power n minus 1. You remember this is the very basic one. Similarly, we are going to differentiate cosine a lot of times in this course. Differentiate cosine, and you know that it's negative sine. You are going to differentiate sine a lot of time in this course. So d over dx of sine x, and you are going to get a cosine here. Similarly, d over dx of ln x, you know that it's 1 over x. Similarly, d over dx of e to the power x is simply e to the power x. This is a very useful one because it's used in the phasor analysis of AC circuits, the last one. Similarly, there are going to be some integrals. Let me put those integrals here for you. So you need to remember the basic one here. Integral x to the n dx is equal to x to the n minus 1 divided by n plus 1 plus coefficient constant. Similarly, you need to differentiate sometimes sine x, which would result in minus cosine x plus constant. You would need to differentiate cosine x, and that would result in sine x plus c. Similarly, you need to remember these slightly more complicated ones. Sine squared x dx integral, and the result will be half x. You can do it on your own as well, but it would be better to just remember this formula. So half x minus quarter of sine 2x plus c. Similarly, integral cosine squared x dx is half x plus quarter of sine 2x plus c. Now, apart from these integration formula, you would also need to use these two basic formula a lot of the time. You remember these are trigonometric identities. I'm discussing them over here with differentiation and integration, but they are essentially trigonometric identities. So you need to use a lot of sine 2x is equal to 2 sine x cos x. This one is going to be used a lot. And similarly, uh, cos A into cos B is equal to half of cos A minus B plus cos A plus B. So with these three prerequisites, our first lecture ends. Let's hope that you are able to understand these concepts. I am going to be giving you uh, ungraded and unmarked assignments and quizzes so that you can practice these things. Inshallah, in the next lecture, we are going to talk about a couple of more prerequisites because I believe you need to understand and revise the electromagnetic theory that you have understood in intermediate, and you also need to revise and understand the the uh, f- you need to understand the electromagnetic theory. We are going to cover that in the next lecture, and we are also going to talk about a lot of, you can say, mathematical concepts that are going to be used in this course. So until then, uh, thank you very much. Please give your feedback if anything bothers you, if anything is wrong, your the audios are wrong or the visual is wrong. Please let me know. Thank you very much, and let's meet in the next lecture.